All right. The next thing we're going to talk about is when we take these, is something called the central limit theorem. Okay? So, what I have here is, these are movie budgets. I don't remember the year, but these are all the movie budgets. So is anybody surprised to see the shape of this, where most movies are relatively inexpensive to make, and then you have your few big blockbusters that are, so we have this, if I ask you to describe the shape of this particular distribution, you would say? Skewed right. In fact, pretty strongly skewed right. And from the summary up here, we can see that the mean is $51.379 million. These are in millions. And that the standard deviation is $57.927 million. Everybody good so far? Now, this comes from a sampling program that I have. So what I did is I took 3 different samples. Each of these are a sample size of 10. Is everybody seeing it? Okay. And these marks right here are my different sample means. Okay? So this is just taking 3 samples with 3 different sample means. What do you notice about the 3 sample means I got here? They're more than different. They're pretty far apart from each other. And if we look at the shapes of these, I know it's kind of hard to see. This one's kind of skewed right, but it doesn't have any of the real high points. This one has way too many high points, right? And the reason this is happening by just chance is if my sample size is 10, it's pretty reasonable I could get an uncharacteristic sample. Is everybody with me? Now, what this picture is down here is not just 3 samples, it is a total of 1,000 samples. So that 70.4 is this one right about here. That 108, that's this one. The 28 is probably around this guy, right? And then I did 997 other samples, and we can kind of see what's going on here. Okay? And for that small sample size, what do you see about the shape of this? This is still skewed right, but is it as skewed as my population? Like if I go back up here, this was really skewed. This, not as skewed. Cool? All right. So, this picture real quick. This is mu, straight mu. It is the mean of all the individuals in that population. This is the mean of the X bars. It's the mean of the sample means. And here's the kicker. If we turn the page again, the big difference. Now my sample size is 100. Look at these sample means. They are, what would you say about them? They're much closer to each other. And as I look at the shapes of these samples, what can we say about the shapes of these samples? They're all pretty skewed right, yeah? They're all, like, these samples resemble the population a heck of a lot better. Okay? So, they're skewed right. And because they all resemble and all have that right-hand skew, the X bars are closer to each other. Now that goes down here. And now, when we look at the sample, that dot plot of all those sample means, what do you notice about this one? So, the population was skewed right. Each individual sample was skewed right, but because all of those sample means are about the same, it ends up being approximately normal. Okay? So back to, essentially, this idea of what we call, so each of these is now the same. Sample means when the sample is 10, sample means when the sample is 50, sample means when the sample is 100. Okay? All right, so as I look at each of these, like the first one seems to be skewed right. The second one's getting pretty close to normal, maybe a little off, maybe. The last one is definitely normal, okay? So as my sample size increases, the X bars get closer to normal. All right, next, I'm going to jump into, this mean is 50.2, 51.3, 51.0. You'll notice the mean of those X bars, and this is going to look weird, is approximately the mean of the population. Lastly, this one, this is the standard deviation of these is called a standard error. It goes from 17 to 8 to 5. So as my sample size increases, all my sample means are closer to each other, which means the overall standard deviation goes down. So this leads into something we call the central limit theorem. Okay, all this central limit theorem says is basically this. As n increases, sampling distributions get closer to normal. Now, there are two situations in which my distribution of means, my sample means, is normal. Either if my sample size is big enough, we can say the sample means will be normal no matter what. And our general rule of thumb, this example notwithstanding, is as long as my sample size is greater than or equal to 30, we can assume X bars are normal. Or if I know the population from which I'm taking my sample is normal, then the X bars will also be normal. Okay? So for instance, if I'm taking a sample of students and measuring their heights, okay, and I want to know what's the probability that the average height of a student, or the average height of 10 students is greater than 6 foot, okay? Well, heights are normally distributed. I don't need a sample size of 30 then because the heights are already normal. If I have a skewed distribution, I need a larger sample size for that normality to show up. All right, so some real quick, a reminder of different notations because there's a lot here. When I say just mu, that is the mean of individuals in a population. When I say mu with this subscript X bar, that is the mean of these sample means. They mean, those two symbols mean two different things. Okay? So to go, those two symbols mean two different things, so they're talking about two different groups. However, they always have the same value. So if the mean of the population, if I say, on average, the height of students is 5'7", which I have no idea what it is, but let's just pretend I say that, okay? 5'7", 67 inches, okay? If I say that, and then I say, what's the mean of all the possible sample means? Guess what it is? Still 67 inches. Are we good? All right. So, please tell me that's everything. Oh, and the standard deviation of the x-bars is how spread out those x-bars are. Yeah, I actually really appreciate it. As soon as I said 5'7", I was like, oh, what did you just do? Thank you guys for being mature. The way you can calculate the standard deviation of the x-bars, remember how I said it gets smaller with your sample size? If you take the standard deviation of your sample, of your population, and divide by the sample size, which, by the way, this formula is on your formula sheet, okay? That'll tell you the standard deviation of the x-bars. So how might I ask you about this? An average sixth grader reads at 10 words per minute with a standard deviation of 11 words per minute. We take a random sample of 60 sixth graders. Okay. So if I want to describe, so first thing I might do is I would call that 10 words per minute mu. Because that's talking about the average of individuals in my population. And then I would describe this 11 as sigma, because it's describing the standard deviation of individuals in my population. And then I would say, as soon as I see my random sample of 60, I would write n equals 60. So as I draw out my as I draw my distribution of sample means, I got to decide, is it going to be normal? Well, I don't know that the population is normal. I do know that my sample size is bigger than 30, so I'm allowed to assume those x bars will be approximately normal. The mean of my x bars is going to be 10 because it's going to match the mean of my population. Though when I write it here, that is the mean of the x bars. The standard deviation of my x bars is 11 divided by the square root of 60. And again, this is a picture of sample means. Which, by the way, 11 divided by the square root of 60 is 1.42. Okay. What is the probability we find a sample of sixth graders whose mean is more than 11? So I want to find the probability x bar is bigger than 11. So I'm going to draw the picture of my x bars. My standard deviation of my x bars is 1.142 or 1.42. And this would be a great example of when I use normal CDF. My lower boundary 11, my upper boundary a gajillion, my mean 10, my standard deviation 1.42. How we feeling? The average age of Columbus State students is 27.4. We take the standard deviation of 5. Again, those are describing entire populations. We have n equals 35. What does n equals 35 tell us? 35 is bigger than 30. I'm allowed to draw this as normal. My mean of my x bars, 27.4. My standard deviation of my x bars will be, what will it be? How do I find it? 5 over square root 35, which, by the way, is 0.845. The picture, by the way, describes it. I can see the shape, the center of the spread. Everybody good? What is the probability? Oh, well, that can't be the question I intended to ask you guys here at all. Let's say, what is the probability I get a mean of 35 students with average of 25 or less? So that'd be pretty surprising. Hey guys, I'll finish that last example tomorrow, and then you'll have the